In the last video, we talked about advection and came up with this main equation for pollution movement downstream. In this video, we're going to talk about pollution spread due to Fickian mixing, or dispersion and diffusion. So dispersion, again, we covered a little bit today in class on, this is Thursday in my world. Dispersion, in this case in rivers, is due to velocity shear, or changes in velocity due to drag along the bottom of the river or along the sides of the river, banks. Again, this is a figure showing you how if you start out with a uniform column of some pollutant over time because of drag, for example, along the bottom of the river, it spreads out. So mixing. We also have turbulent diffusion that's due to channel irregularities and sort of random movement of water. And then we also have molecular diffusion, but it's considered fairly unimportant in rivers. It's also the slowest, as we talked about today as well. Okay, so this is just an example of the transport of a solute in a stream, and you've done a bit of this in class, at least with a tracer that you can't see, but you use a conductivity measure or a meter to kind of see its transport downstream. This is rhodamine dye. You can see it getting added here and sort of slowly becoming more and more spread across the stream. This is sort of the second picture of it. And then here it's spread all the way across the channel and it looks much more diluted across down the length of the channel. And that's pretty standard river mixing procedure. So this is showing you that sort of process in a graphical sort of cartoon, starting with sort of consolidated pollutant here, getting spread out, becoming more dilute, and spread across the entire channel. So again, spreading in rivers due mainly to dispersion, that's this sort of idea, and also spreading around rocks and that sort of thing, and then turbulent flow of water. So on average, chemical concentration or pollutant concentration in a river is normally distributed. And this works to our advantage when we're trying to predict where pollutants are going to go. But why is it normally distributed? So if you remember back to your stats, I think most of you have had some stats up to this point. Fickian mixing, that is dispersion and diffusion, are essentially random processes, and random processes create normal distributions. And just to remind or convince you of that, here's a little animation of this. We'll start it up. So this is a random ball drop going down these pegs, so the balls sort of randomly go to one side or another, and you can see them sort of falling down. And this is a rather slow video. I'm going to speed it up so you can see the more balls you have falling down here, the more normal this distribution on the bottom starts to look. Again, large sample size helps you out with this. Okay, well, you can see it sort of starting to form a normal distribution there. If you'd like to, you can follow the link and follow it to as far as you want to go. Okay. So in this picture, you have about a 50-50 chance of going right or left at each peg. So it's a random process, ends up creating, here you can see I took it out to about 2,000. You have a nice random distribution here. Okay, so on average, chemical or pollution concentration in a river at any given time is normally distributed. So spreading increases the distribution width, so you can see that over time. This is sort of the time 0. It's kind of a narrow distribution. Time 2, it's a little bit wider. Time 3, it's even wider still. And it also reduces the peak concentration, or the maximum concentration, which we're going to call C max. Okay, so we can use the properties of these normal distributions to estimate spreading rates. So here again, we have the peak at the center of the distribution. And the pollutant is symmetrically distributed around that Cmax. At each time point, this is the case. So here we have sort of a standard normal deviation or normal distribution. And again, we have symmetrical distribution around the Cmax, or the maximum point here. And we can use the standard deviation of the distribution to estimate spreading around Cmax. And this comes from sort of your basic stats. So if you remember, one standard deviation on either side of the mean captures 68% of all points. Two standard deviations on either side of Cmax, in this case, captures 95% of the cases in the distribution. Three standard deviations captures almost 100%. But we're going to focus on this 95%. So we're going to say, if we're looking at the distribution of the concentration of river, two standard deviations on either side of Cmax captures 95% of the pollution in the river at that time point. So this is just showing it to you sort of in that same cartoon that we've been looking at. If this is 95% of the pollution in the river at this third time point, that's two standard deviations on either side of Cmax. And that's going to be 95% of the pollution in the river at that time point. So at each time point, Cmax, which is the maximum concentration, it has a location x in the river. So here's your T1 measurement, and here's sort of the normal distribution characterization of that time point. And it declines at each time there. And each time point has a spatial variance that is associated with the standard deviation. So if you remember what a variance is, it's the square root, or it's the square of the standard deviation, or put in another way, the standard deviation is the square root of the spatial variance. So if we know the spatial variance of the concentration of the pollutant in the river, we can get to the standard deviation. And then we know that 4 times the standard deviation captures 95% of the pollution spread within the river. So that's 2 times the standard deviation on either side of Cmax. Okay, so then just another way of saying or looking at the fact that the peak concentration, or the maximum concentration, declines over time. So this is one time point, another later, and then another time point even later. And at the same time, the spread of the distribution increases. So the distribution becomes wider. So you can look at that as the spread increases, the spatial variance increases, or the standard deviation increases over time. So we characterize this spread using the longitudinal Fickian mixing coefficient, or DL, and that's in units of area per time. And this is just to show you that the same thing, that all these things that we've just talked about, is also true for the data that you guys collect in lab. So this is lab data from 2013, and you can see that you've got a declining maximum concentration in conductivity, and you've also got an increasing spread. So not very much spread at this time point. A little bit later you've got bigger spread, and even later you've got much larger spread. Okay, so what do we want to know about a chemical that gets spilled in a river? So first we want to know about the maximum concentration. What is the maximum concentration, and where is the maximum concentration? And these things change over time. So the location changes over time, moves downstream, and the maximum concentration itself declines over time because of spreading. So how quickly this declines depends on river mixing rates. And again, that's talking about the Fickian mixing coefficient, DL. So faster mixing means a faster decline in the maximum concentration. So we can estimate DL with dye experiments using concentration data, and it varies by river or reach. It does not vary across chemical. So it's a function of the river itself, not a chemical. Okay, and here is the equation for that. It says DL equals the spatial variation, or spatial variance, which is the standard deviation squared, over 2 times the time after that pollutant was added to the stream or river. And I'll give you guys an example of this in a different video. Okay, so then we can use DL to calculate where or what the maximum concentration is at the time that we're interested in, the time after injection. So we need to know, for that, we need to know the initial mass of chemical per area, cross-sectional area, and what time we're interested in, and we need to know the longitudinal Fickian mixing coefficient. Okay. The other thing we want to know is where is most of the pollution. We may know about Cmax, but then how far away from Cmax is the pollution? And we can use DL to get information about this using the standard deviation. So here we can use this formula. If we know DL and we know the time that we're interested in, we can rearrange the equation to solve for the standard deviation. And then we know that 2 times this standard deviation on either side of Cmax, which we know, will contain 95% of the chemical in the river. So that way we know where Cmax is, and then we know how far on either side of Cmax has that pollution spread. Okay, so just keep in mind this is 2 standard deviations on either side of Cmax, so it's 4 standard deviations total. Okay, so this kind of sums up where we are at this point. I know it's a lot of equations at this point. We've got the advection equation, and then we've got spread due to dispersion. So we've got this DL, the mixing coefficient, and then we've got Cmax. And we can use both of these things together to figure out what is the maximum concentration, and then where is 95% of the pollution in the river. And that is that for now.